All right, good afternoon. Today, we will start a new chapter on gravitation. Gravitation is something you have learned in your high school curriculum, physics curriculum. It's about Newton's law, which describes the attraction force between two bodies with masses. So we are going to describe that law in more details, and we are going also to use that law to formulate it, to calculate the force, the gravitational force due to an extended body, in particular spherical object. We will calculate the gravitational force inside and outside of a spherically symmetric mass distribution. We also would apply the law of gravitation together with the law of motion to describe the motion of a body around another massive body. That is what you commonly do when you describe the motion, say, for the moon, the planets around the sun, and also the motion of the stars, etc. And our discussion will be slightly more general than those in high school. In high school, we only have circular motion, circular orbit. Now we extend our discussion to a more general elliptical orbit, which is the general cases for all the closed orbit motion. So let's start. First, we would like to know the form of Newton's universal law of gravitation. It says that two masses, we should emphasize that the 2-point mass. Newton didn't say anything about extended body. For the extended body, you have to do integration. So to have a good beginning, we start with point mass. For 2-point mass, that is, the size is negligible compared with the distance, then they attract each other with a force that is proportional to the masses and is inversely proportional to the square of the distance. So this is a law. Okay. Sometimes this force law is called the inverse square law force because the force F is proportional not to R, but to the inverse of the square of the distance. Okay, the inverse of the square of the distance. So it's sometimes called the inverse square law. Okay, so when the distance is double because of the square, the force decreases by 4 times. If the distance is triple, then the force will decrease by 3 to the 3 square. That is 9 times. And G is a constant called universal gravitational constant, and it takes on such a value in SI unit. Now this is the SI unit for the G. You can actually easily find it out by using dimensional analysis. It's not that difficult. F has a unit of Newton, and the mass has a unit of kg. That's why we have kg minus 2, and the distance has the unit of meter. So we have meter square here. Okay. Now, strictly speaking, the law is valid only for point masses. The force on extended body, if you want to find that, you need a integration. Now, for example, let's consider the gravitational force between a point mass, which is a very small mass here, and an extended body. Now, why is it not obeying the law of universal gravitation like this? The point is because extended body have a distribution of mass over space. So different segment, different tiny volume in this distribution, they have different distance. This dm will have a distance r from the point mass m, right? But another tiny volume, which I call the m prime, the mass I call the m prime, will have a different distance r prime from the point mass. So I don't know, actually, I don't know what r to use. What r should I use, right? Different element in the distribution have different distance from the point mass. So according to the law here, The law is true for this pair and also for this pair. But the R are different, right? So I cannot use a single R in this equation to represent the gravitational force of the whole object on this point mass. I cannot do that. The only way that I can calculate that is to do an integration. I should integrate all the dm. I suppose that the m is here. I put the dm here. And I integrate over all the r square to get the total net force. And that is what is required for integration. Now, but there is a special case. The special case is that if you have two spherical objects, spherically symmetric object. Now, this is not necessary for the two objects to have a uniform mass distribution. The mass distribution the density of the object can be a function of the radius. Okay, so you can have an object that is more dense at the center and less dense at the outside. But as long as the distribution is spherically symmetric, the distribution does not depend on angle, then the two bodies attract each other in a way that exactly obeyed the Newton's law of universal gravitation. But we should interpret the R very carefully. The R is actually the distance between the center of that two spherical objects. Now, but that requires integration. Newton, after doing a complicated integration, he finds that for a spherically symmetric object, the Newton's law of universal gravitation does hold. Okay, so that is the triumph of using integration. Now I should write for convenience of calculation. I may like to write the gravitational force in vector form. Now suppose I have the sun located at the center of a coordinate system, and it attracts a planet. The planet has a mass mole m and is located as a point xy in this coordinate. So the position vector of the planet is the vector that points from the sun to the planet. I call that vector r. So the unit vector is the r vector divided by its magnitude. Okay, I call it r hat. The symbol hat at the top of the symbol hat at the top of a letter always means a unit vector, a vector with unit length. So I use the vector divided by its length. I got a unit vector in the radial outward direction. But the gravitational force is attractive, right? So the planet is attracted towards the sun instead of outward. So I add a minus sign here. The minus sign denotes that minus r hat is the distance. So it denotes that the gravitational force is towards the sun, is towards the coordinate origin. Okay. Now, how do I write this unit vector in terms of the Cartesian component? Well, I know that the vector r itself is xi plus yj. This is the position vector in terms of the Cartesian basis, I and j, the unit vector, right? But how about the r? Well, r is x squared plus y squared square root. The distance between the sun and the planet is simply by Pythagoras theorem, x squared plus y squared square root. Now, this form of Newton's laws of universal gravitation allows you to resolve the force into two components. Now, if I put this guy back to this equation, I can separate the x component and the y component. Because if you have an additional x here and additional r here, so this becomes r cubed. We have r squared here, so together with this r, I have r cubed. And for the x component, I have x. For the y component, I have y, right? So the x component of the force becomes something like this, and the y component of the force becomes something like this. Okay, and do not forget the r here is not a constant. The r here is also a function of x and y. Okay, so it depends on x and y. Now, this form is useful for numerical calculation. In your project, you will be given a task to calculate the motion of a planet around the sun. but the motion is not a circular orbit. The motion is an elliptical orbit. You are going to solve that elliptical orbit by using numerical method. You don't know how to solve it analytically now, but you can solve it numerically and verify that it is indeed a ellipse for the planet going around the sun. Now, so in your calculation, when you are doing an ellipse, for ellipse, the planets, the distance between the planet and the sun keep on changing, right? Sometimes it's closer to the sun and sometimes farther away from the sun. So R does change because X and Y change and R the distance also changes. It's not a circular orbit. So you should allow X and Y to be the variable. Okay, so both R and X and Y, they are all variable. So you keep in mind you have this changes to obtain a elliptical orbit. Now the gravitational force is universal. What is meant by universal is that any object exerts a force on another object. So any object that has a mass exerts a force on another body which also has a mass. Okay, so massive body with a mass exert gravitational force on each other. Okay, so and that's mutual. What is meant by mutual? The force exerted on the two bodies in a pair of gravitational interaction, they are equal and opposite. So they form an action-reaction pair. If the Earth attracts the moon with a certain gravitational force, then at the same time, the moon also attracts the Earth with the same but opposite gravitational force. So the interaction, the two forces form an action and reaction pair by Newton's third law. Okay. Now, in the history, there are a lot of observation about the motion of the celestial body, especially the planets, how the planet move. That is a very important problem in the, say, mid 16th or 17th century, because that is an important problem in physics. And Newton solved that problem. So Newton proposed that the universal law of gravitation. But the point is, we actually relies on the sun's gravitational force to verify that law. Okay. In order to verify Newton's law of gravitation, we assume the sun attracting the Earth and the Earth attracting the moon. But actually, we don't know what the mass of the sun is. So that cannot be so we cannot use the mass of the sun to know what the gravitational force is. Gravitational force is quite difficult to generate in our daily life, except the gravitational force of our body on our body by the Earth. But the Earth, the mass of the Earth is also not known. So there is actually no ways for people to know the actual value of the gravitational force. Now the sun and the Earth, we know that they produce gravitational force, but there is no other means to measure their mass, right? Except looking at the gravitational force. But for the gravitational force, we don't know the gravitational constant, right? So how do we define know that gravitational constant? How can we use a laboratory scale experiment to measure a very tiny force in a very small scale to find that gravitational constant? That is a very very difficult problem in the say 18th or 19th century. And Cavendish, English physicist, he managed to do that. Okay, in the old days. Okay, how did he manage to do that? Now he used practically this setup. We have two balls here with mass capital M, and another. Now they are balanced on the pivot. It's fixed to the pivot. There's another pair of balls of mass small m, each of mass small m, is hanged by a thin fiber. Okay, you have a thin fiber hanging these two balls. So the two balls can be rotated about this axis, about the fiber. Okay, because of the gravitational force between the two masses here and the two masses here, there will be a torque that tends to turn this rod around. and that will twist the fiber. When the fiber is being twisted, there will be a restoring force, restoring torque, balancing the torque due to the gravity. Okay, so that's why you can use this fiber, a very thin fiber, to measure the tiny torque produced by the gravitational force. Now that is a very difficult, technically very difficult thing in the old days, but Cavendish succeeded to do that. Okay, and he actually verified that the force is inversely proportional to 1/r² in the laboratory scale, not in the astronomical scale. In the astronomical scale, that's easy. You can observe the planet and you see that obey inverse square law of force. But in the lab scale, the objects are so small, the mass of the object is so small, the attraction force between them is very small. If you consider, for example, these two mass has a mass of 1 kg, then they are separated by 10 cm. Then the force between them is of the order of 10 to the power minus 8 Newton, which is extremely small force. And you couldn't measure that very small force, except you use a very thin fiber to produce a very small torque that counterbalance the torque produced by the gravity force. So that is things Cavendish achieved. And in a modern version of this experiment, we commonly adhere a mirror on the fiber, so that if you have a laser source, this is a laser source, shine on this mirror, the reflections of the spot of light will be on the scale. So when the mirror turns a little bit, that turning motion will be amplified, and you can see the diffraction being amplified on this scale. So that makes the measurement easier. Okay, and actually, in a physics lab, we are going to do this experiment. Okay. Now, surprisingly, if the mass is spherical, as I say, the force is exactly 1/r², and that is Newton's achievement. That is to use integral calculus to analyze the gravitational effect of extended body, based on a law that is applicable only for point mass. So that is a success for integral calculus. I don't know if I have time to talk about this integration in detail. The integration is somewhat difficult, so I put it at the end, and hopefully after going through all the important concepts, I still have time to talk about this difficult integral to let you appreciate it. But in the course of our discussion, I will assume this to be true, and to proceed with some of the example. Now then we come to the concept of gravitational potential. I think this concept you already have learned, because you already have learned potential energy of gravitational force when we discuss about work and energy in chapter 5, right? So essentially that gravitational potential is just gravitational potential energy. It's just the same thing. The gravitational potential is the work done by external force in bringing a mass from infinity to the present position. Do you remember when we talk about work and energy, we integrate, we use the external force that just balance the gravitational force, and we integrate that external force from infinity to the final position to calculate the gravitational energy on the object, the potential energy of that object. Do you remember that integral? Now we do the same thing. It's actually the same thing, but we do it on the unit mass. So what is meant by gravitational potential is a kind of potential energy for a unit mass. Okay, the potential energy per unit mass is the gravitational potential. Okay, so the gravitational potential energy and the gravitational potential, they just differ by the mass. If you divide that energy by the mass, you get the potential. Okay, so it is the potential energy per unit mass. Now for a point mass m, these are the point mass, right? So for point mass m, we integrate the force per unit mass from infinity to r. We divide the F with the small m, with this mass. So in the expression, we get rid of the small m. Now do not forget the minus sign, because we are integrating the external force that just balance the gravitational force. So we are holding that object and with the external force, and we integrate that external force that just balance the gravitational force from infinity to the present position. So this is the expression. So that's why we have a minus sign. Now, so integrating this will become Gm multiplied by minus 1 over r. Now, why do we choose to integrate from infinity? Because at infinity, 1 over r is 0. So we get rid of the constant term. And eventually, we get a potential that depends only on, with one term, that depends only on r, as minus Gm over r. Okay. Now, the warning is that do not be tempted to obtain the potential by multiplying the force by the distance r. This is not the correct derivation. We have mentioned it in chapter 5, right? Now, this is the potential. Essentially, the curve, the shape of the curve is just the same as the potential energy. Okay, it is 1 over r as negative. Okay, so it diverges when it approach the origin. Okay, and of course, as I say, the energy and the potential, they are just related by the mass. Okay, u and v are they just differ by the mass m. Now you should be careful. In my derivation, I leave the capital M here. So this potential, gravitational potential, should be regarded as the effect of the mass capital M. The small mass M doesn't matter. It's a test mass. Okay, the V should be regarded as the effect of gravity due to the large mass capital M. Okay, so this is the potential of the large mass. Okay. Now we can also calculate the gravitational field strength. What we call the gravitational field strength is the gravitational force per unit mass. Again, we divide, we calculating things per unit mass, F over M to get G. Okay. But as we know, the gravitational force is the minus the spatial derivative, the derivative of u with respect to r. Right? Now, this is a standard relation between what? Between the potential energy and the conservative force. The conservative force is negative, the derivative of the energy, potential energy with respect to distance. Okay, so F is equal to minus du dr. But I noticed that now you are calculating the force per unit mass, right? So if you have u divided by m, I got v. So it becomes minus dv dr. So the derivative of the potential with a minus sign is a gravitational field strength. Now, why do I use a symbol G for this field strength? Field strength actually means the intensity of the gravitational field at a certain distance from the source, right? That is called the field strength. But why do I use the symbol G? G seems to be a symbol used for acceleration due to gravity. You use this symbol in your high school for acceleration due to gravity. Now, I will show you that this is in fact the acceleration due to gravity. Why? We have this relation already. Now, because if you have an apple at a distance r from the center of the Earth, the gravitational force is gmm over r squared. That is inverse square root of force. But if you divide by the mass m, you got the gravitational potential, gravitational field strength, right? But what is that? What is the force divided by m? The force divided by m, by Newton's second law, it is just the acceleration, right? It is the acceleration on the apple due to the gravity. So the gravitational field strength is nothing but the acceleration due to gravity. Okay, and it happens that when the F is divided by m, the acceleration is independent on the small mass m. Okay, it only depends on the large mass, but it does not depend on the small mass. So it is a gravitational acceleration or the gravitational field strength here at this point. Okay. So we have this. Okay. Now, so let's have a very brief summary of what we have learned in the previous chapter. In the chapter of work and energy, we already have learned these two relations, right? If you have a gravitational force, you like to integrate it with a minus sign from infinity to r, and you get a gravitational potential energy, right? And if you have the gravitational potential energy, you take the spatial derivative with a minus sign, you go back to the gravitational force. Okay, so from the gravitational force to energy, you need an integration. And from the energy to the force, you need a differentiation. Okay, so these are the relation between the two guys. Now the gravitational force per unit mass will become the gravitational field strength. I call the gravitational field strength with a symbol G. And the gravitational potential energy per unit mass is just a gravitational potential V. Okay, and the two quantity G and V, they are related in exactly the same way as U and F. Okay, because each of the quantity you take per unit mass and you obtain these two quantities. So they of course are related in the same way as the force and energy. Okay. And to bear in mind that why we use the symbol G is because the gravitational field strength is the same as the acceleration due to gravity at that position. Okay. Now we handle the situation of spherically symmetric mass distribution. I prefer not to start with a difficult mathematical proof using Newtonian integration. That would be difficult and that would obscure the simple physics. So I better leave it maybe at the end of the chapter. I want you to see the physical picture first to let you have an understanding using a simple line field pattern to let you understand why the force is so. Okay. Now I think you have learned this kind of figures before. Gravitational fields or electric fields or magnetic fields, they can be represented by field lines. You just draw the field lines, right? Now for a point mass or for a small spherical mass, you can imagine that the gravitational field lines is converging towards it. And the converge of this field line is even in all directions. Because the mass is spherical, the distribution is spherical, it's a point, right? So there's no distinction between this direction and that direction. So the field lines must be converging. And you draw an arrow towards the mass to denote that the field lines is converging to it. So the force is directed because of gravitational force is always attractive. So the field lines is already directed towards the mass. Okay, so this is how you represent a gravitational field of a point mass. Okay. And in drawing the picture, if you have a larger mass, then you have to draw more field lines. Okay, suppose you have two masses, one of a larger mass and the other of a smaller mass. There will be more field line converging to the larger mass than the smaller mass. Okay, so the greater is the mass, the more field lines is converging to it. This is a graphical representation. Okay, you represented a larger mass here, the effect of a larger mass. Now, there's also another representation about the field strength at a certain position. The gravitational field strength is actually the field lines per unit area. Okay, it is not the number of field lines, but the field lines per unit area. Now, how to understand it? Suppose at a certain distance from the point mass, I now has a small area. This circular disc is a small. Imagine this is a small area. And when I place this small area perpendicular to the field lines, I would intercept some field line, right? The area will intercept some field line. Now let's say at this position, the area intercept 2 field lines. Okay, 2 is just any number that used for easy understanding. Okay, so let's say 2 field lines is now intercepting this area. So the line density, the area density of the field line is the 2 field lines divided by the area. Okay, say, okay. So, but how about if I put this area now closer to the point mass? If I put the same area closer to the point mass, because the field lines is converging, right? Now there would be more field lines passing through the area. Okay, suppose here at this position, new position, we have 4 field lines passing through the same area. So if I represent the gravitational field strength by the field line density, I will have to say the gravitational field strength here is double that of the O position. Okay, so that is how I represent the field strength. When the field lines is getting close, when you have more field line intercepting the unit area, you have a stronger gravitational field. Okay. Same area intercept more field line, you have a stronger gravitational field. So the field strength gets stronger and stronger when you are getting close to the point mass. Does it make sense? Now, you may say, well, that's a concept is really vague. I cannot understand it. How do you count the field lines? That is not that make no sense. Now, don't worry about it. We will have if you study electromagnetism in year 2, I will teach you how to represent the number of field lines by a more precise mathematical language of surface integral. But that is another matter. In the time being, it is sufficient for us to use this picture to derive all the phenomena about gravity that we need. Okay. Now let's derive the inverse square law force using the concept of field lines. Now I have a point mass here, right? So all the field lines are now converging to this point mass. And I want to know the field strength at the distance r from the point mass. So I draw an imaginary sphere. That is a spherical surface of radius small r. Now this sphere, it does not exist in the real world. I just imagine now I have a shell, spherical shell, encloses the point mass at its center. And the radius of the shell is r. Okay, the small r. And as I say, the gravitational field strength here is the number density of the field line, the number of field lines divided by the area, right? So how many field lines are intercepting this area? I count the field lines, but I know I cannot count the field lines, but I know that the number of field lines is proportional to the mass. If I have a larger mass here, I have more field lines converging to it. So although I don't know the proportional constant, I know that that is proportional. So the number of field lines is actually a total number of field lines produced by the mass is actually proportional to the mass itself, right? So field lines, number of field lines is proportional to mass. The area at the radius r, which is the area of this spherical shell, is 4 pi r squared. That is a standard expression for the area of a sphere, right? Now, so you see immediately you see the field strength is proportional to m over r squared. Okay, the r squared comes out naturally if you regard the field strength at the field line density, then it comes out very naturally. The field strength is what m over r squared. Okay, and if you accept this, and in the SI unit, you may like to add a gravitational constant in SI unit, then you got the expression gm over r squared. Okay, so that's why I tell you about this picture. It's easy to understand, right? So we derive the inverse square law force from the picture. Of course, that is not a derivation, but that is an easy way for you to understand it. Okay. why the inverse square law will hold this way. Now then we will talk about an important theorem in gravity. Let us call that is a shell theorem. A shell means a spherical object, a hollow spherical object. It's very thin, so all the mass is concentrated at the surface. The center is hollow. Okay, so you imagine a spherical hollow object, and that is a shell. Okay, a spherical shell. Now, the problem is, if I imagine the spherical shell now has the same mass as the point mass. Both of the mass is m. This point mass have a mass m. This spherical shell also has a mass m. Then I would like to ask, what will then be the distribution of the field line inside and outside the shell? Okay, do you understand my question? If this shell has the same mass as the point mass here, then what will be the distribution of the field line? How would the field line distribute outside the shell and inside the shell? Now, first, we may like to know the distribution inside the shell, if there's any. Okay. Now, because now the problem is spherically symmetric. Okay, is symmetric in every direction. So if the field line exists inside, okay, it will be either pointing outward or inward, right? But since the mass is concentrated on the surface, then we expect something like this. We expect the field line to be, if there exists, the field line must be pointing in this direction. It must be pointing outwards. Okay. But if the field line points outward this way, then we extend it backward to the center. The field line will be meeting there, right? So that will be a center giving out infinitely strong field lines. Because at the center, there will be all the field line concentrated. So the field strength here will be infinite. Is that right? If my representation is correct, then the field strength at the center of the shell will be infinite. Okay, but there's nothing at the center. The shell is hollow, right? So I cannot imagine if there is a hollow shell, I can have an infinitely strong gravitational field at the center. Nothing is giving out the gravitational force, right? So that does not make sense. But if that does not make sense, that means this field line does not exist. And if this field line does not exist, I just erase it. And if I erase it, that means there is no gravitational field inside the shell. The gravitational field inside the shell is simply 0. Okay, that is the necessary conclusion. So where does the field line goes? The field line must be on the outside. It must come from the outside, and all the field line must terminate on the shell, just like here. Okay, and because the mass are the same, the mass of the shell and the point mass are the same, I expect the same number of field lines coming from infinity to terminate on this cell, right? So that means the gravitational field outside the shell is the same as if all the mass on the shell is concentrated at the center. If I'm looking at the outside and I measure the gravitational field there, I cannot distinguish whether it comes from a shell or come from a mass of the same mass at the center of the shell. I cannot distinguish that. I simply will see a point mass gravitational field of the same strength. Okay, so that is an important consequence. Okay. Now you may not be convinced about having a 0 gravitational field inside the shell, But Newton, Isaac Newton, in his book of Principia, he actually present another proof. Now suppose this is a uniform shell, and I now has a point here inside an arbitrary point inside the shell. Okay. Suppose I draw two cones. I have a small, two small narrow cones in the opposite direction. This cone originates at this point with a small angle diverging, and it intercepts, eventually it goes to the shell, and it intercepts the shell at a small area. I call this area A1. And the opposite direction, there's another cone which obtains the same angle, the same solid angle, and it intercepts the shell at another area, which I call A2. Can you imagine this? You have two ice cream cones. Okay, imagine two ice cream cones, but the ice cream cone is very narrow, very small, and they diverge in opposite direction. Okay, one ice cream cone intercepts the shell as area A1, and the other ice cream cone on opposite direction intercept the shell as area A2. And the distance between this point and these two areas are R1 and R2 respectively. Okay, now so the mass on shell on the area A1 to the mass on the area A2 is M1 over M2, right? The ratio of the mass, right? But the mass is proportional to the area because the shell is uniform. So the mass must be proportional to area. So M1 over M2 must be equal to the ratio of the area, that is A1 over A2. Okay. Now, but this is a cone. The cone has the same, these two cones actually has the same angle at the vertex. So they are similar to each other, right? And if they are similar to each other, the area that is intercepting should be proportional to the square of the distance, the square of the height of the cone. So A1 divided by A2, because of these two similar cones, the A1 divided by A2 is equal to R1 square divided by R2 square. Does it make sense? Now, so when we arrange this formula, we find that M1 over R1 square is just equal to M2 over R2 square. But if I multiply two sides by the gravitational constant G, they are just the gravitational force produced by these two areas at this point, right? M1 over R1 square is the force produced by this area at this point. M2 R2 over R2 square is the gravitational force produced by the second area and also at this point. And the two forces are opposite in direction. And if they are equal in magnitude, then they cancel each other. And I can imagine the shell to be consist of a lot of such pair on both sides. And in each pair, the gravitational force in each pair cancel. All the gravitational force will be canceled in pair. And eventually, the force at this position will be zero. So that completes the proof. That is Newton's proof. Okay. So we have an important result. The important result is that if I have a spherical shell, a uniform spherical shell, then the gravitational force inside the thin uniform spherical shell is strictly zero. The field strength is zero. And outside the shell, the gravitational field outside is the same as if that of a point mass located at the center. So it takes such a value, minus Gm over R square. I can imagine that all the mass of the shell is now located at exactly at the center. And it just produces the same field strength, okay, at the point mass. Okay. So do you understand this theorem? Okay. Now I base on this result, and I can work. I can work a lot of problem. Okay. Now let's take a look at the field inside and outside the shell. Inside the shell, the field is strictly zero. Okay. outside the shell, the field is just like a point mass. So it's given by minus GM over R squared. So it looks like something like this. And of course, on the shell, the value is minus GM over capital R squared, where capital R is the radius of the shell. Let's take a look at the potential. The potential is the integration of the G minus G from infinity to the final position. So integrating this from infinity, minus sign, integrating from infinity to the present position will give me minus GM over R, just like a point mass. We did it before. It's just a point mass thing. Okay. So if the field is the same as point mass, the result must be the same as point mass. So I know there's the field, the potential outside is minus GM over R, the point mass result. How about the inside? If I find the potential inside, I have to integrate all the way from infinity to a point that is inside the shell. But if I integrate all the way from infinity to the surface of the shell, I got the value of potential minus GM over R, capital R. If I further integrate inside, because the G is 0 anyway, so I got the same value. Because the G is 0, so I don't got any additional thing if I integrate inwards. So the potential inside will then be a constant, and that constant value will be equal to the potential on the surface, which is minus GM over capital R. Okay, so you have a constant potential here. Okay. Now I will finish this part before letting you have a break. Now I'm done with one shell. For one shell, I know how to calculate the force inside and outside. The force inside is 0. The force outside is the same as if the shell is a point mass, right? So how about a spherical mass distribution? Imagine now, the spherical mass distribution can always be thought of a superposition of many, many thin shells. I can imagine there are many, many thin shells added together to form a spherical object. And if my mass, my small mass, is lying out of this distribution, then all the shell will produce a gravitational field. That is like a point mass at the center, right? Because each shell is producing a gravitational field just like a point mass at the center. So if I have a lot of such a shell, all the shells is producing a gravitational force just like the point mass at the center, then a mass at the outside will feel a gravitational force just like a equivalent point mass capital M at the center, right? So the gravitational field of a spherical object is the same as the gravitational field of a point mass at the center. It doesn't make any difference, right? So that is the result. That is the important result. The important result is that if I have a spherically symmetric object, the gravitational force produced by this object to a point outside is just the same as all the mass of the object is concentrated at the center as a point mass. Okay, so the force is strictly minus GMM over R squared. And it holds even if the density may not be uniform. Now, if the density depends on the radius only, but independent of the angle, I can still think of the object as being consists of a lot of shell, uniform shell, and so that the same theorem holds. So this will hold. This theorem will hold even if the density is a function of R. If the density is larger at the center and smaller at the surface, this theorem still holds. Okay. Now, in the next lesson, let's break for 10 minutes. In the next lesson, I will teach you how to use the theorem that we arrived before to calculate the gravitational force on the small point mass m that's located inside a uniform solid sphere. Now we have a solid sphere filled with mass, uniformly distributed with mass. And we want to calculate the force on the small point mass m inside the sphere. Okay.